Good morning, students. So we are going to discuss a few basic concepts of this particular chapter in physics today. It will be a very short video, basically clearing a few doubts about the very basics of the word refraction. Okay, so refraction, as we all know, if we talk in terms of refraction in light, it is essentially the process of the bending of light. Okay, now when that happens, how does that happen, why that happens, all that is going to be discussed in this particular video today. So let's say, for example, when we discuss the word refraction, so we say that it is the bending of light. Now basically what actually happens is, when does this process take place? Suppose that I give you a separate surface of separation. Let's say this is a surface of separation between let's say medium 1. So I'm going to call this as medium 1. Okay, and this is an optical medium. An optical medium is any medium through which the light can pass. Okay, so let's say we have over here we have the medium 2. Okay, so these are two different media. Okay, and the light will be actually passing from one medium to another medium through this surface of separation. So this is in fact if you no, refraction is the process, it's a surface phenomena. Okay, so whatever happens, whatever slowing down of speed, whatever bending of light takes place, it initially starts to take place from here. Okay, which is the surface of the separation. Okay, so let's suppose there is a ray of light. Okay, so let me draw the ray of light first, the usual way in which everyone draws it. This is the usual way in which you will see, even most of the books also mentioning it, most of the teachers mentioning it, that this is the way a ray of light approaches. Okay, so let's say that it is traveling in one medium 1. Okay, and now it has come. Now see, as long as it was traveling in the same medium, it was going along the same path. Okay, and suppose the velocity, let's say if this medium was air, suppose, or vacuum also you can say, so the velocity of light would be 3 into 10 to the power 8 meters per second. Okay, roughly. Okay, in fact this is the speed of the light in vacuum. Okay, so let's say, for example, that this is the scenario. Now the moment it strikes over here, what will happen is, see, we will not go according to any rules as of now. We will first try to understand what actually happens when something is moving on, let's say, a particular kind of a road. Let's say this is a particular kind of a road. Okay, let's say a smooth road, or a a road which does not have a lot of obstructions, lot of traffic on it. Okay, so it's like, this is a path, this is a region where you can easily and smoothly walk on it, or take your bike, or your automobile, whatever. Okay, so you can keep on going in a particular direction because there is really no obstruction. But the moment it reaches over here, now you see this is medium 2 altogether. Okay, so this optical medium has different sets of characteristics. Maybe it is rugged, maybe let's take the analogy of walking on a road again. Now this was a smooth road, but this may not be that smooth. Okay, so this may have rugged edges, this may have stones on the path, this may have a lot of obstructions, but still the movement has to take place. Okay, so there will be some effect on that particular kind of motion which was undergoing in this particular medium. Okay, so there has to be some slowing down of your automobile. Okay, so if we talk in terms of the automobile again, if we talk in terms of the normal movement of a bike on any particular surface, so what is it subject to? It is subjected to the kind of road on which it is traveling. Okay, so if this medium 2 is slightly rugged, has more optical density, let's say the density of the material on the road is more, there are a number of jagged edges to the stones on the road, not properly built. Okay, so what is going to happen is, the speed with which the light was traveling, or the speed with which the bike was traveling, will reduce. Okay, so it will have to reduce. So this is only considering that I am going from let's say a rarer medium. So this was a rarer medium, and this is a denser medium. Remember, we are always talking not in terms of the generic literal rare and denser medium in terms of density. We are talking in terms of optical density. I'll explain the difference also in a little while. So the speed of the light has to slow down in this medium, okay? But again, when we talk in terms of the process of refraction, we say that there is bending of light taking place. So let's say that if we draw a normal, let's say that this is the normal drawn to the surface of separation between the two media, okay? So let's say, for example, this was the angle that was there, okay? So supposing that let's say this was the medium, this was the angle of incidence I, okay? So this was the angle at which this particular ray of light was coming with regards to the normal, okay? So will it continue to go in the same direction? No, because we say that this is a process of refraction taking place, so the light has to bend, but nobody really cares to explain why the bending should be there. See, you can let's say, let's talk of an example over here. Suppose you are moving on a road like this, okay? Now this part of the road is clear, so you are going with a much faster velocity, but supposing over here there is a lot of traffic, so you will have to slow down, okay? So this slowing down can happen in the same direction itself, right? You really don't have to bend anywhere, okay? So that's the logic that we are going to discuss upon. So why do we say that the light, let's say for example, when it reaches here, it has to bend like this? See, the rule says that whenever we are traveling, whenever we are sending light from a rarer medium to a denser medium, it will bend towards the normal. So where is the normal? This is the normal. So you can see that the actual path of the ray was this. So had this separation not been there, the ray would have continued to go straight like this. But no, has it really gone straight? No, it has bent. It has bent. Where? You can see that it has bent towards this particular direction. So let me first draw, let's say this was, if this was the actual direction, let me just so let's say for example, if this was the original direction of the ray, okay? So the ray should have continued to move in this direction with a little smaller speed or the lesser speed, but no, it has, you can see that it has bent also, it has bent also. So what is the reason why this bending takes place? Okay, so for understanding this, we have to have a look at what is known as the wave nature of light. Okay, so let's say for example, I'm going to draw another diagram here which will be slightly different from the one that I drew just now. So let's say for example, we have this as the surface of separation. Now you see, the main mistake that we actually make here is that we keep drawing straight lines whenever we want to show a ray of light. So a ray of light is not literally in terms of a single straight ray. Okay, light travels in the form of a wave. Okay, so let's say for example that this is a wave which is traveling. Okay, so let's say, let me draw this. So let's say that this is a light wave which is coming. Okay, so it is going to travel like what? It is not going to travel like a straight line or a pointed arrow or something like that, but it is traveling, let's say, let me shorten this in terms of the length so you understand it better. Let's say that this is that particular wave which is coming. So what is the direction of approach? This is the direction of approach. Okay, so this whole thing that I have drawn, this is the wave form, this is the light wave form. Okay, so this is going to travel in this particular direction, but the only difference is that it is not traveling in the form of a straight line, it is traveling in the form of a wave. So when it is traveling in the form of a wave, it's not a singular point which gets in contact with the surface. There are so many points you can see on this particular wave. There are different points that are going to get in contact with the surface, but not at the same time. Now you see, what I'll do is I'll assume that this particular wave is traveling forward. So I'm going to continue to draw this. I'm going to continue to draw this particular waveform as it approaches the surface. Okay, so let's say that it is approaching. So you can see that the direction of the wave travel is towards the surface of separation. This is the surface of separation, this is the rarer medium, okay, and this is the optically denser medium. Okay, so this is how it is going to travel. Now you can see that if I had drawn a single arrow, pointed arrow like I had drawn earlier, then you would see that there is only one point of contact on the surface. But as you can see, when the light is traveling in the form of a wave, what actually happens is, and it is traveling at in a slant direction to the surface. So what is going to happen is, not all the points on the waveform are going to get in touch with this particular surface at the same time. You can see that this part of the wave, the left hand side of the wave, is the one that is going to make contact with the surface first. So let me draw it once more over here. Let me bring it a little more closer. Now you can see that this part of the wave has already made contact with the surface of separation. So what has actually happened is that this part of the wave here has already met that obstruction which lies in that second medium, which is the denser medium. Okay, so there are, let's say for example, not so smooth a road over here. So while in all the different cases over here, each part of the wave, light wave, was traveling in the same direction with the same kind of speed all the time, but the moment it reaches here, this part of the wave has to slow down now because it has met the obstruction already. Whereas what is happening with this part of the wave, has it really met the obstruction just now? No. So it is going to continue to travel with a larger speed, the earlier larger speed, whereas this part of the wave is going to slow down because it has already met that obstruction. Okay, now imagine if there is a body of this particular size and this particular length, one part of the body has already met the obstruction, whereas the other part of the body has not met the obstruction, and this part of the body is continuously moving still with the larger speed, whereas this has stopped, not really stopped but slowed down. So don't you think that this part of the wave will try to cover a larger distance because it was traveling with a far more velocity, whereas this part of the wave over here, it has to slow down. So this part is moving slowly, whereas this part is moving fast. So effectively what happens is that brings about a turning effect. Okay, because this is a whole body which is traveling and all the parts of the body are connected to each other. So one part is moving with a slow speed, the other is moving with a larger speed. So what is going to happen? The part which is traveling with a larger speed will cover far more distance, so it will come forward, whereas the distance traveled by this end will not be that much. So now when you discuss it in terms of a single ray of light, you say that along with the slowing down of the speed, what actually happens is the bending also takes place. The bending also takes place because this is the reason why the bending takes place. Okay, so I hope you have understood this much. Now let's move ahead to a small question based on the same concept. Okay, so here is that question. A ray of light strikes a glass slab at an angle of incidence of 30 degree. Okay, so let's say that we have a small diagram over here. So this is the air medium from which the ray of light is traveling. So let's say it is traveling like this. So if we draw the normal is going to be drawn like this. This angle is what we are calling as angle of incidence I. Okay, so we can straight away see that that angle I is given as 30 degree. Okay, so where is this ray of light going to travel to? It is going to travel to a glass slab. Okay, so let's say that this is a glass slab over here. Okay, this is a glass slab. So what is going to happen? Is the speed of light going to slow down? Yes. Then rarer to denser medium, the speed of light slows down and it bends towards the normal. So let's say for example, it has bent towards the normal. So this is the normal, it has bent towards the normal. So this angle R is what we have to find out. You can see, find angle R if the refractive index of the glass is 1.5. So you all know that the term mu, this term is known as mu. This is the refractive index this is used to represent the refractive index. So you can see that mu value is 1.5 for the glass. Okay, so based on the Snell's law, we are going to try to solve this particular question. So let's say what is the Snell's law? Let us first write that down. So according to the Snell's law, we have refractive index is equal to, what do we have? We have sine of I upon sine of R. Okay, now please note that this is this term actually is unique. This is refractive index of what with respect to what? That is something that is important. So we have to say that refractive index of the second medium with respect to the first medium. This is always written like this. Okay, refractive index of the second medium with respect to the first medium. So what is that second medium? The second medium is glass. What is that first medium? The first medium is the medium in which the ray was already traveling. So it is air. So it is this portion that you already know the value of. So they have given it as refractive index of the glass. Obviously it is with respect to air, so that is why they have not specifically told you this. Refractive index of the glass is 1.5. So 1.5 is equal to sine of I. Now what is I? I is 30. So sine of 30 upon sine of R. Okay, so it is essentially this R that we have to find out. Usually what happens is that you get a value which is which extrapolates into a particular fixed standard angle R, but then here we will see what happens based on the calculation. So let's say for example we have 1.5 is equal to sine 30 is half, so you have this over here upon sine of R. Okay, so you can see that I have put sine 30 is half, so I have put the value as 0.5. So sine R comes here, so I am going to solve it here. Sine of R is equal to 0.5, and this 1.5 comes down in the denominator over here. So it is simply the readjustment of this particular thing. So this and this, you all know, 5 3 is a 15. So you have 1 upon 3 as the sine R value. So essentially what happens is sine R becomes, when you divide 1 upon 3, you will get 0.3333 and so on. Okay, so it is roughly like 0.333. Now this is not a standard value. Okay, so what is that particular value of angle R for which the sine gives you this? So this is really not standard. So you'll have to make use of the mathematical trigonometric table. So I'll show you exactly how it looks over here. So if you see, you'll go to the natural science portion. I'll show you this up close so that you understand. See, this is the natural sine page that you have. You'll find it in most of the class 10th and 12th maths books. Okay, so what do you have to look for? You see this column, you can see that it is x degrees. So this is the angle that is mentioned. Okay, but we don't know the angle, we have to get the angle. Okay, the value of that sine of that angle is known. So what is that value? You can see the value is this 0.333. so where is that 0.33? Can you have a look? Let me just show you this with the help of a pen over here. Let's say for example we are looking for 0.3343. so you can see that this value over here, is the closest to what we have. We have 0.3333 and this is 3333. Please note that these columns you may not be you may not be able to see that decimal, but that decimal is always there. They have only showed it in the first column, second column over here, 0 point, 0 point, 0 point. You can see all these are also carrying that 0 point. Okay, so 0.3338 is as close as possible to our value. So what we will do is we will check horizontally. What is the angle over here? The angle over here is 19, but had it been only 19, then sine 19 would have been this value. But our value is not this value, our value is this value. So along with going in the horizontal direction and finding out this angle, you also have to go vertically up like this to see that this is 0.5 in terms of degrees. Okay, so what will happen is your angle whole number is 19, and along with that you will put 0.5. so essentially what that gives you is your R value. Let's say for example, if I write the R value over here, you will see that we will have R value will be from sine R. Sine R value was 0.3333. So what will be your R value? You have looked up in the trigonometric table, you have found it to be 19.5 degrees. Okay, so it is 19.5 degrees. So I have basically showed you the way in which we have to have a look at the trigonometric table in order to find it out. Okay, so let's say for example this is 19.5 degrees. Once again, let me show you how you come to this particular value of angle R. You come to this value with the help of your natural sine table. Why sine? Because you can see over here it is sine. The value of angle of sine of that angle is 0.333. So you have to look for that particular value, or whichever is the closest. So 3338 is the closest. So correspondingly you look at the angle here, and vertically also when you go up you see half degree over here. So 19 over here and half over here will make it 19.5 degrees. Okay, so hope that helps. Hope you have understood the essential reason why the ray bends and how do you use the Snell's law for the calculation and all.